What's up, everyone, and welcome back. Today we're diving into one of the most mind-bending, jaw-dropping subjects in all of science, black holes. These are the universe's most extreme objects, and trust me, by the end of this video, you're going to look up at the night sky very differently. So buckle up, because things are about to get wild. So let's kick things off with the big picture. Black holes represent the absolute extreme limit of gravitational collapse. Think of them as the universe's ultimate crushing machines. They're born from the life cycles of massive stars, and once they form, they create astrophysical phenomena so weird that they literally challenge everything we know about physics. Understanding them isn't just cool. It's crucial to understanding the universe itself. Alright, so the first question we need to tackle, and honestly the question that started it all for most of us, is what actually is a black hole? I mean, we've all heard the word, but do we really know what we're talking about? Let's find out. Here's the deal. A black hole is a region in space where gravity is so intense, so ridiculously powerful, that absolutely nothing can escape it. Not particles, not dust, not even light. The fastest thing in the universe. It forms when a massive star runs out of nuclear fuel, collapses under its own weight, and creates an infinitely dense point called a singularity. Let that sink in. Infinitely dense. Now you might be wondering, okay, but how does something like this actually happen? Great question. The birth of a black hole is actually a 3-act story, and every act is more dramatic than the last. We've got stellar collapse, a supernova explosion, and the formation of a singularity. Let's walk through each one. Stellar collapse. Imagine a star many times more massive than our Sun. It's been burning nuclear fuel for millions of years. But nothing lasts forever. When that fuel runs out, the outward pressure that's been fighting gravity just stops, and gravity wins. The star collapses inward on itself in a catastrophic gravitational freefall. This is the critical first domino. The supernova. This is where things get absolutely explosive, literally. When the outer layers of the star come crashing inward, they bounce off the incredibly dense core and get blasted out into space. We're talking about an explosion so powerful it can briefly outshine an entire galaxy. This cataclysmic shockwave tears the star apart and reveals what's left behind at the core. The singularity, now the core, stripped of everything around it, keeps collapsing. It doesn't stop. It can't stop. It just keeps crushing inward until it reaches a point where density becomes infinite and gravitational pull becomes infinite. This is the singularity. A place where our known laws of physics completely break down. And surrounding it, the boundary of no return. A black hole is born. Now here's something a lot of people don't realize. Black holes actually come in different sizes. We've got 3 main types. First, stellar black holes, formed from individual star collapses. Then, supermassive black holes. And we're talking millions to billions of solar masses here, lurking at the centers of most galaxies. And finally, intermediate black holes, the mysterious middle child that scientists are still trying to fully understand. All right, let's talk anatomy. A black hole has 2 key features you need to know. Number 1, the event horizon. Think of it as the ultimate point of no return. A spherical boundary where escape velocity exceeds the speed of light. Cross it, and you're not coming back, no matter what. Number 2, the singularity at the core, where gravity becomes infinitely strong and space-time curves infinitely. Physics just gives up and says, nope, I don't know what's happening here. Okay, so what actually happens if something falls into a black hole? Glad you asked, because this is where it gets truly bizarre. We're talking spaghettification, time dilation, and physics that completely breaks down. These aren't science fiction concepts. They're real, predicted phenomena. And honestly, they sound like something straight out of a Christopher Nolan movie. Yes, you heard that right. Spaghettification. As an object approaches a black hole, the tidal forces become extreme. Gravity pulls much harder on the side of you that's closer to the black hole than the side that's farther away. The result? You get stretched vertically and compressed horizontally like a piece of cosmic spaghetti. It's simultaneously one of the most terrifying and funniest sounding things in astrophysics. Now, time dilation. This one will genuinely mess with your head. Near a black hole, gravity is so immense that it actually warps the fabric of time itself. Time passes more slowly the closer you are to the event horizon. So if you were watching someone fall toward a black hole, they'd appear to slow down and freeze at the edge. Meanwhile, from their perspective, time would feel completely normal, right until it doesn't. Einstein predicted exactly this in his theory of general relativity. He was right. And then we hit the wall, inside a black hole, beyond the event horizon, and certainly at the singularity. Our two greatest theories of physics, general relativity and quantum mechanics, flat out contradict each other. Neither one works on its own. We genuinely do not know what the laws of physics look like in there. This isn't a gap in our knowledge, it's a chasm. And it's one of the biggest open problems in all of science. So here's the obvious problem. Black holes are, by definition, invisible. They don't emit light. You can't just point a telescope at one and say, gotcha. So how on Earth, or rather, how in the universe, do scientists actually detect them? Well, it turns out there are some incredibly clever methods, and the numbers behind them are absolutely staggering. Gravitational waves. When two black holes spiral together and merge, they send ripples through the fabric of space-time itself. Gravitational waves. Over the last decade alone, scientists have detected 1.5 million of these waves from black hole mergers. 1.5 million, and these waves travel across the entire universe before reaching our detectors here on Earth. That's mind-blowing precision science. X-ray emissions. When gas and matter spiral into a black hole through what's called an accretion disk, they heat up to millions of degrees and blast out X-rays with a power of 10 to the 38 joules per second. To give you some context, our sun produces about 3.8 times 10 to the 26 joules per second. So we're talking about something radiating 1 trillion times more energy than the sun. Scientists can detect these X-ray bursts from across the galaxy. Star tracking. Here's an elegant approach. You can't see the black hole, but you can see how it affects everything around it. Scientists have tracked over 1,000 stars orbiting near supermassive black holes. By watching those stars whip around at incredible speeds in tight orbits around what appears to be nothing, we can infer the mass and location of the black hole with remarkable precision. Absence, it turns out, is very revealing. So to sum it up, 3 powerful methods: gravitational waves at 1.5 million detections, X-ray emissions at 10 to the 38 joules per second, and over 1,000 stars being tracked near supermassive black holes. Together, these techniques have turned black hole detection from science fiction into hard science. And the data keeps pouring in. Now let's get personal. There are 3 black holes that have become absolute rock stars in the astrophysics world. You've probably heard their names: Sagittarius A star at the center of our own Milky Way, M87 star, the first black hole ever photographed, and Cygnus X-1, one of the very first black holes ever discovered. Let's meet each of them. First up, Sagittarius A star. This is the supermassive black hole sitting right at the heart of our Milky Way galaxy, just 26,000 light-years away from where you're sitting right now. It has a mass equivalent to about 4.1 million suns, 4.1 million solar masses, and it plays a pivotal role in governing the movement and behavior of billions of stars in our galaxy. This thing is basically our galaxy's anchor. Next, M87 star. This is a historic one, located 55 million light-years away in the Virgo galaxy cluster, M87 star made history in April 2019 when the Event Horizon Telescope captured the very first image of a black hole's event horizon ever. That orange glowing ring you've seen everywhere? That's M87 star. The image took the work of over 200 scientists and effectively turned a black hole from theoretical concept to photographic reality. Truly iconic. And last but absolutely not least, Cygnus X-1. Located about 6,000 light-years from Earth, this was one of the first black holes ever discovered back in the early 1970s. It's part of a binary system, meaning it's in a gravitational dance with a massive blue supergiant star, stealing gas from it and producing intense X-ray emissions. For decades, Cygnus X-1 was the black hole that scientists used to understand how these objects actually behave. A true pioneer. Okay, so we know what black holes are, how they form, what they look like, and where they are. But here's the question that I think is the most important of all. What do they actually do? What is their role in the grand scheme of the cosmos? Because it turns out, black holes aren't just passive voids, they're active architects of the universe. Black holes are fundamentally woven into the formation and evolution of galaxies. They regulate star formation rates, too much star formation in a region. The black hole's energy output can shut it down. They drive galactic winds that push gas across hundreds of thousands of light-years. They influence the orbital motion of every star around them. In short, without supermassive black holes at their centers, galaxies as we know them simply wouldn't exist. These aren't just holes, they're engines. Now for the wildest twist in this whole story. Can black holes die? Yes, but it takes an almost incomprehensibly long time. Stephen Hawking proposed that due to quantum effects near the event horizon, black holes can very slowly emit radiation, now called Hawking radiation. Pairs of particles form near the event horizon. One falls in, one escapes. Over unimaginable timescales, we're talking longer than the current age of the universe, a black hole gradually loses mass and eventually evaporates completely. Even the most powerful things in the cosmos have an expiry date. We're almost at the end of our journey through the cosmos, but before we wrap up, let's zoom out one more time and think about where all of this science is heading. Because honestly, we've only scratched the surface, no pun intended. The research into black holes is far from over. In many ways, it's just beginning. Future space missions, next-generation gravitational wave detectors, and more powerful telescopes like the James Webb Space Telescope are all aimed at peeling back more layers of these cosmic mysteries. Every answer we find opens 10 new questions, and that's what makes this the golden age of black hole science. The universe is talking. We're finally starting to listen. And that's a wrap on our deep dive into black holes. From stellar collapse to event horizons, spaghettification to Hawking radiation, we covered it all. If your mind is spinning right now, that's completely normal. And actually a sign that you've just touched one of the deepest edges of human knowledge. If you learned something today, smash that like button, subscribe for more cosmic adventures, and drop a comment below with your biggest black hole question. See you in the next one.